I will discuss this thing of the concept of an open system. So in a system that is not closed, but is interacting with something bigger outside it. And finally, I will discuss the model we have analyzed and the results we have found. The point is that all this thing is quite mathematical, so I don't like it usually, but I will need to use some mathematics in the talk. The first two parts of motivation and symmetries in open systems, I think they can be understandable for somebody who has a background in physics. The last part about model and results, maybe it's a bit more for people of open quantum systems, but okay, but it's the talk, so you can just ask during the talk if you have any doubts, okay? So let's start with the motivations. Okay, we always start with a qubit. We always like a qubit that is the simplest model, a two-level quantum system. Why do we like it so much? Well, basically because on one hand, it's a simple approximation of many quantum systems, and in one case, it is a quantum system. The spin of a particle is a qubit, a two-level system. Then it's the basic unit of a quantum computer, so for all the thing of quantum computation, if you want to understand quantum computation, we need to understand how a qubit works. And finally, it's also important to study fundamental phenomena because, okay, it's given its simplicity, maybe we can understand some fundamental stuff on the qubit that on bigger system would be too complex to be studied well. This is very abstract, but how do we find a qubit in reality? Okay, nowadays in a quantum lab, there are many possibilities of having a qubit, basically because of quantum computation, so all the hype for it has created a lot of different qubits. And I'm presenting this thing now is what is called a superconducting qubit. You see, it's something mesoscopic in the sense that it's on this chip, but I think it's 1 millimeter, so something that you can see, almost see. Then, okay, you need some big stuff to cool it down, to keep it properly. So, okay, it's bigger than 1 millimeter, you see. But what is a superconducting qubit, and how can it be such a simple two-level system, given that it's so big? Well, it's the same thing of flocking. Here at IFISC, we know, well, flocking. What is flocking? Well, it's the fact that a lot of birds, if they decide to move all together, to do the same movements at the same time in the same way, they finally behave as a single bird. And, right, I mean, this is flocking, very naively. But a superconducting qubit is exactly the same, but with atoms. So if you have a lot of atoms, very cold atoms, in a superconducting state of a superconducting material, if they are in a superconducting collective wave function, they can stick together, they do not excite one from the other, and they can move together as if they were one single atom. And in this case, we can actually see this collective property of a material as one single qubit. And for instance, here it's an experiment that they do at Aalto University in Helsinki. These are two superconducting qubits connected together, and this is an experiment to study the heat transport between some qubits, so quantum heat transport, thermodynamics at the very quantum level. What's the matter? Why am I talking about this? Okay, because I need some motivation to introduce open systems. What is an open system? Well, a superconducting qubit is always interacting with something bigger than the other qubit, for instance. Why? Well, because, for instance, there are thermal particles that are not avoided, and they hit against the qubit, so there is some heat. Or there is the electromagnetic field that is fluctuating on the qubit, so it's creating some noise. And what is it? Well, it's the so-called quantum noise. It's something that is bigger, it's coming from outside, it's interacting on the qubit. So it's what creates what is called an open quantum system, because we cannot describe the qubit and the electromagnetic field and the thermal particles and so on as we do in thermodynamics, if you want. But we want to study still only the qubit, but we have to take into consideration the fact that the qubit is immersed in an external environment that is surrounding it. And not only this, but also sometimes, like in this case, you see this, this red and blue stuff, they are some resistors, like literally the resistors that you play with in the laboratory of physics at the university. And what they do, what they simulate is exactly what we call a buff. That is, again, something that is external from the qubit, and it's, let's say, hitting the qubit with a lot of modes, like a lot of particles hitting the qubit to simulate a buff, exactly as the standard buff, as when you put the hand on the boiler and it gets hotter. I mean, it's the same. There are a lot of particles sitting against it, and here the effect is the same. So, and why do they do it? Because they want to study thermodynamics. That is something that must consider something bigger outside that is a buff. So this is the motivation why we want to study open system. So just to have now a formal framework about it, because now I won't go back to something physical, let's say. Let's go to the abstract part of what is an open system. So there is an overall state, rho SE, that is made of the environment and the system in red. So the system would be the qubit, and the environment would be the field outside, and so on. We can consider just the state of the qubit by doing this operation that is called partial trace, and it's the equivalent of doing a classical marginal distribution. So what we want to study is just the system, it's not the overall. So we do this, and we study just the state of the system, but you see that it depends also on the state of the environment. We may do the same thing for the environment, but we are not interested in it, of course. So we have a controllable system here, immersed in a bigger environment that is something that is like non-interacting infinite number of modes, again, like the thermal particles. And we can recover the state of the system. But now, how does the state of the system change during time because of the environment? How can we describe this? What we use is what we call a master equation. You see, it's this thing. You see that here I'm not considering the overall state. I'm just considering the state of the system. And this is, if you want, a differential equation for the state of the system only. And it's driven by this superoperator, because you see it's an operator that it's applied on the system, so it's a superoperator in this sense. This superoperator has all the information about the interaction between system and environment. And this is what is called a Markovian, in this case, master equation. This is what we basically study every time in open quantum systems. You see, it's something that is actually very, very simple, after all. I mean, it's a very simple differential equation. It's an I mean, the solution is an exponential. And all my talk now will be about this Liouvillian superoperator and the symmetries of this Liouvillian superoperator in some physical situations. But now, to talk about symmetry, let's go back to the standard course of quantum mechanics.
Your system, are you also considering the particle exchange between the system and environment?
Yeah, otherwise they do not interact, right? I mean, of course, they are interacting. Yes, I mean, it's a way of interacting, and yes, they can exchange particles, let's say.
So the number of particles on the system is conserved or
No.
not?
This will be important in the talk, actually. So later on, I will discuss about it. So symmetries in closed system. As you may remember, I mean, there is this very famous Noether's theorem that is connecting what is a symmetry and what is a conserved quantity in classical physics. And now I'm using the language of quantum mechanics, but it's the same in classical physics. What is a symmetry? Well, it's something like this, a one-parameter group of transformation, of unitary transformation. J is an observable, so something that we can measure. And a symmetry is this thing, is the fact that we can transform the Hamiltonian with this transformation, and we still get the same Hamiltonian. So it's what we call a symmetry. What is a conserved quantity? Well, it's an observable whose value does not change a long time. Again, this is standard, something that is conserved, right? And we know that a symmetry is equivalent to a conserved quantity for Noether's theorem. Just a couple of examples. The standard one, the free particle. This is the Hamiltonian of the free particle. This could be classical mechanics. Again, it's something very, very easy. The Hamiltonian commutes with the momentum, of course, because it's free particle. There is nothing inducing a force on it. And what does it mean that it commutes? Well, of course, that the momentum is conserved, so that is the velocity is the same along the time for a free particle. We can build this transformation, but of course, is also symmetry, right? For the fact that the momentum is conserved. What does it mean? It means that this transformation, that it's the famous translation in space, that is like this. What does it mean for the wave function? Well, that if we take a wave function, and if we translate, and then we translate the wave function, so we get this psi d x minus phi, we get a new wave function, but the new wave function is different from the one before, but it's still an eigenfunction of a Hamiltonian with the same energy. You see, this is the standard eigenfunction of the Hamiltonian. A translated one is still an eigenfunction with the same energy. And this is the point about symmetries, right? That if you have a solution, then you can move along this solution, and still you're remaining in the same solution of a Hamiltonian. You're not changing your energy. The other example would be the particle in a central force field that is basically hydrogen atom. Here all the momenta commute with the Hamiltonian, and then we can build this one parameter group transformation. And what does it do? Well, it rotates the spatial coordinates, polar coordinates, so it's a rotation in space. And again, what does it mean? That if we rotate things in the solution of a Hamiltonian of a hydrogen atom, if we retain the eigenfunction, we still get a solution of a problem. And okay, so you see, this is all about conserved quantity and symmetry. But now, what happens in an open system? This is the point. That could be something interesting, I think, also in classical physics, but I do not know anything about it. So maybe, I don't know. There are equivalent theorems, but this is only for quantum. What is the problem now? That we have a master equation. The dynamics is completely different from before. So what's the meaning of a symmetry here? Okay, and things get a bit tougher in the sense that we have to introduce what is called the adjoint representation, that maybe you have heard about it. What is it? Well, the point is that we have a symmetry like before, that is this one. You know, this is an operator. This is the symmetry that we were discussing before. Only on the system. This is a symmetry on the system of the operator. Now we have to introduce this calligraphic Q that is a superoperator, and it is defined like this, where O is a general operator on the system. So this is the definition of this superoperator U. And you see, again, I'm using calligraphic letters for superoperators, so things that act on the operators. You see the L here is calligraphic, the U is calligraphic. While I'm using standard letters for things that are operators, that act on the system only. Okay, so this is a way of passing to a higher dimension and to think at the level of superoperators and to find the symmetry there. What's the point? The theorem here is that, you see, let's consider this. This is what is L would be now the new H, the new Hamiltonian. Before, the dynamics was driven by the Hamiltonian, now it's driven by L. So this is the symmetry now, you see? It's a symmetry on the superoperator. It's all calligraphic. And we are living in a higher dimension space. This was the old conserved quantity, so the observable that does not change in time. You see, the point is that there is no connection here. The message is that there is no direct connection between a symmetry on the superoperator, so a symmetry now in our system, and the conserved quantity. Yes?
Sorry, I'm a bit lost. Like you have a conserved quantity in your system or in the environment, or
yeah, yes.
That you can measure in the system that is conserved.
Exactly, because now you see, when I use this thing of superoperator, I'm forgetting about the environment. Now, all the things I say are all of the system, because the environment is, let's say, there is this marginal distribution that you do, and so you forget about the environment, and the environment, let's say, is hidden here in this superoperator that is driving the system. It's like before it was the Hamiltonian, now it's something different because there is the environment, but still you forget about the environment. Okay. So you see, there is this difference. Now, okay, for the experts on the topic, there is actually an extended theorem that says that if we take this GKLS form of the master equation, there is the Hamiltonian, the jump operators, and if everything commutes, then we recover, let's say, Noether's theorem. So we have conserved quantity and symmetry at the same time, but otherwise no. Okay, this is something for an expert of open quantum systems. Don't worry if you don't understand this.
Sorry.
Yeah.
Like your conserved quantity, you have a conserved quantity associated to this supersymmetry.
No. This is the point.
Okay.
I mean, there is the symmetry that is this definition. Then I will give an example of what is this. And there is this could be, I don't know, like the momentum of before in the Fourier particle. This could be the fact that the momentum is conserved. But if the system is open, there could be that the momentum is conserved, but you cannot build a spatial symmetry. There is no spatial translation on the system, something like this. Okay, and in my talk, I will focus on this part, because what I'm interested is in finding the symmetries of this Liouvillian superoperator. Okay, so now I go to the model. The model is a model of some, yes?
Why the symmetry is not a conserved quantity?
In the talk,
Yeah.
Yeah, because it happened that we studied that. I mean, it happened that we have run into this symmetry of a Liouvillian superoperator, and that the conserved quantities are not involved here. But of course, it's something.
Simplifies maybe your calculations in some cases?
The symmetry? Or yes, that's what I will see. The conserved quantities are important for the steady state, for instance, the coherence species and so on, because it's, yeah, I think they can be seen as sort of integrable of motion of your system, but this is not the case, because there is this sort of striking thing that you can have a symmetry, but there are no integrable of motion. Okay. So my model is some non-interacting quasi-particles. Now I will say what they are, but okay, I have depicted them here. You see, these nice circles here are quasi-particles, and they have different dimensions because I allow for different energies of quasi-particles. What are quasi-particles? They're just, I mean, things that you can write as independent particles where these things are bosonic or fermionic operators. For instance, I mean, the easiest thing I can think of that are quasi-particles are the light that come out of a flying disk. I mean, photons are quasi-particles. The photons of light, I mean, they are actually particles, but they are not interacting quasi-particles, right? They are photons, there are a lot, they have different modes, and in the sense that there is a particle that is going here and one in the other direction, they have different energies. Well, here it's all green, so maybe the frequency is more or less the same. But this is what I'm talking about, more or less. Okay, a laser is, if you want, one quasi-particle, or also like the fermionic particles of a material. I mean, the material is full of electrons. Electrons are fermions. If there is a case in which they are not interacting, then we can say that they are not interacting quasi-particles. Or also chains of qubits. In some cases, they can be seen as interacting quasi-particles because you can rewrite everything like this. So my model is made of these interacting quasi-particles that you can think of exactly as, light coming out from a flying disk that you see every day. And the conditions I want for my model is that there are stationary paths in the sense that these environments interacting on the particles. You see these nice circles of yellow, red, and orange around the particles. It means that there are some external environments, for instance, thermal field, electromagnetic field, that are acting on the particle. It's just a general thing, and they are stationary, that is the classical sense, so they do not depend on time. I want the interaction between these fields and the particles to be weak. So this is the condition, and this is the standard condition for having a Markovian master equation. And then, okay, a bit more complex, I want a linear coupling in the fermionic or bosonic operators between field and quasi-particles. This is sort of a strict condition. Yeah, what I'm going to say holds for a lot of conditions which are not this strict, but okay, I'm not getting into the details, and it's all in the paper if you're interested. But okay, just consider a linear coupling for now. Okay, now there is a part that is a bit tough mathematically, so okay, I apologize for this, but we want to consider the master equation. You remember, the master equation is what is describing the evolution of the system. You see this time evolution. It's what is given by the Liouvillian superoperator, the famous thing that is driving the dynamics now. The form of the Markovian master equation in general, you derive it and you get to this situation, where these are some function of the environment, and these are what they call the jump operators. They describe the excitation or the excitation that you can create in the system. Okay, later on I will make examples about it. In the case of linear coupling, they are just linear combination of the fermionic or bosonic operators. And what is important is that this omega is the energy gap associated to the excitation of the system. So if this thing is creating a particle that has an energy of omega, for instance, so this omega and omega prime are the energies which are important here. What's the point? The point is that here we have this term. This term is the standard fluctuating term that is very important for doing the rotating wave approximation. If you know, the fact that if things here in the master equation are rotating fast, then they are negligible in the dynamics. So if this difference between omega prime and omega is big enough, all the terms here can be deleted. This partial secular approximation means this. But we delete all the terms here which are not slowly rotating, but rotate fast. But you see that if these operators here creates a particle with omega or with omega prime, you see that but this thing and this thing here, this jump operator and this jump operator must create or destroy the same number of particles. Why? Because if this creates two particles instead of one, and this only one, well, more or less this will be something that is, this energy will be 2 times the energy of a particle that you have created here. Right, because if this creates 2, the omega is the energy gap of the creation. So if you create 2 particles, it's double energy. And here you only have 1 particle, so it's one energy. What does it mean? That omega is 2 times omega prime, and this thing is very big. and it's fast rotating, and you delete it, okay? This is very technical, I know. Doesn't matter if you don't get all the details, just take the idea that these jump operators must create or destroy the same number of particles. This is creating here on the cat of the density matrix, and this is creating on the graph because it's the adjoint. But the message is this. This thing of partial circular approximation have been analyzed in many papers. For instance, this one is a new mathematical formalization that is very nice. And we have studied it in this paper about the local versus global that I spoken about some months ago. So, okay, just take this message now. What do we want to do? We want to search for a symmetry given by this fact. So what I'm going to do now, I define this n. This n is the number operator. You say it's counting the number of particles in your system. For instance, I don't know, if you have a laser, you say, okay, I have 8 photons here. 8, you see, more or less this. This is exactly what is doing this number operator. Okay, we were looking for a symmetry, so we can start by generating the symmetry on the operator level. This is the old symmetry of closed systems. Okay, this is the one parameter same group generated by the number operator. But we know that we are in open systems, so we have to go for the adjoint representation. And we get this thing where you see that is like this, but there is a calligraphic n here. So it's a superoperator of this n. You see, so it's a higher dimension in which we are going. How do we get this? Well, it's generated by this number superoperator that can be shown that acts like this. So if you give a state to the number superoperators, it returns the commutator between my number operator and rho s and the state. So you see that this number superoperator, what it's doing, it's basically if you have a density matrix and if you write it in the basis of excitations of my system, so the basis of how many photons do you have on the, in your state, well, this is doing this thing with the commutator, so it's n rho s minus rho s n. What does it mean? But if you think about it, it's basically computing the number of particles in the ket of the density matrix minus the number of particles in the bra, right? N rho s minus rho s n. Again, I will make examples about it at the end. But you see that this is the point. It's computing number of particles in the ket minus number of particles in the bra. But so let's suppose that I apply the number superoperator on a state. And then I apply my master equation, that is my Liouvillian superoperator. And I get something. And now I do the reverse. I apply my master equation, so the Liouvillian superoperator, on the state, and then I apply n. Does it change the value? Well, the point is that if they create or destroy the same number of particles, here it's creating a particle in the ket, for instance, but this thing is creating another particle in the bra. For instance, +1, +1. So when you compute the number superoperator, it's the difference between these two. So it doesn't change this difference. The number is still the same. Okay. I don't know if you are fully convinced, but this is the point. So what does it mean? It means that it doesn't matter if I apply before n and then the master equation, or before master equation and then n. And this is the result. That is, on the superoperator level, the Liouvillian superoperator, you see the one that is driving the master equation here, commutes with the number superoperator. Or if you want, we have a symmetry, what was before a symmetry on the superoperator level of the Liouvillian superoperator, where the symmetry is generated by this number superoperator. And okay, again, what does it mean that we have a symmetry on the superoperator level? Because, I mean, literally, what does it mean in our system? Because, for instance, we can take a very common system that a lot of you study here at IFISC, a laser. We know that a laser is basically one mode of the field. It will be one quasi-particle, a laser mode. We know that in the regime in which the laser is very weak, it's always dissipating into the environment, okay? Because there is heat, there are a lot of stuff, there is an electromagnetic field going on it. So the laser is dissipating, it's losing energy normally. Yeah, more or less. In open systems, we know that this is the master equation to describe the dissipation of a laser. But what happens that with this master equation, of course, this is impartial circular approximation, so you can trust me that the symmetry is there. There is this symmetry on the superoperator level. But if you have a laser and you start a laser with 10 photons, and you are in the lab, you're doing your experiments about reservoir computing with laser, and you have 10 photons, and then there is dissipation, and you wait a bit, and it's dissipating all the energy in the field, in the external field, and at the end you look and you get 0 photons. Right? I mean, it's something that can happen in the sense that you are dissipating, you lose the energy. What does it mean? It means that we have a famous symmetry, but you see that it's one of the cases in which there is no conserved quantity. The n operator is not conserved. So what does it mean to have a symmetry on the superoperator level if it's not conserving our number of particles? And okay, so the utilitarian now may come and would say, why have you done all this if it's all for nothing? I mean, why do we need all this? Okay, the point is that a symmetry on the superoperator level is useful, as Rodrigo was suggesting before, because we can simplify the master equation, because we can find a block structure of my Liouvillian superoperator that is reproducing this symmetry, because if they commute, they have the same eigenvalues, so we can label all the vectors with the eigenvalues of n, of the n superoperator. You see that here I'm doing something that, again, it's a bit mathematically technical, that is, I'm writing this superoperator as a big matrix. Before it was just a superoperator, an abstract object there in the space of superoperators. Now I write it as a big matrix acting on a vector that is given by the density matrix of the system. So I'm doing this operation, then I will explain a bit with an example that maybe is better to look. What happens is that this matrix here is block diagonalized by the symmetry. So there is a big reduction of a dimension of the problem that we have to solve, basically of a differential equation. To solve a differential equation, we must diagonalize this Liouvillian superoperator. If it's written as small blocks, it's way better than a big block. The other, let's say, important result is the fact that we have a unique steady state. What is a steady state? Is the state to which we are going during the evolution. It's what would it be the equilibrium state of classical thermodynamics. I mean, we are going and we get to a state. This is what statistical physics is about, more or less. So it's very important, this thing of a steady state in quantum physics, both for thermodynamical reasons, so because it's important to understand where you are going with your qubits, but also for fundamental reasons. Because in quantum statistical physics, there are some things which are still unclear, while in classical statistical physics you get more or less all. So it's important to understand which are the steady state we are going to. And if we have a unique steady state that is defined like this, the fact that the Liouvillian superoperator is not making it evolve, in the sense that, of course, it stays there, because it's a steady state, it's equilibrium. Well, this unique steady state is all contained in the block with n equal to 0. So again, there is a big reduction on the search for the steady state of the system. Okay, now I will finally go to the example so that everything can be clearer. We consider a general 2-qubit scenario that we have studied in the paper of local versus global, so the one I mentioned before. But in particular, we take a very, very simple scenario. So 2 uncoupled qubits in a common bath. What does it mean? That we have 1 qubit, a second qubit, that could be like 2 atoms. And they are immersed. There is no direct coupling between them, so they do not know nothing, one of the other. And they are immersed in the same environment. For instance, the electromagnetic field fluctuating in the same way over the 2 atoms. This is a common bath. Okay. This is an open system, of course. There is a common bath. There is a way of writing this master equation in partial circular approximation. It's contained in our paper, and it's this. So if you remember before when I was discussing the technical details of a partial circular approximation, there was these jump operators. Now these jump operators here are these things. So they are sigma minus, sigma plus. So they are the operators creating an excitation in the spin or destroying an excitation in the qubit. So only 2 systems, the operator is doing bloop, bloop, like spinning the direction of the qubit, okay? So we get the master equation in partial circular approximation, so the symmetry holds. Now, how can we describe it? Well, let's take a basis of my 2 qubits. The simplest one is to see the 2 qubits as 2 fermions, in the sense that you can have this fermionic basic of 0, 0, all the qubits down in the ground state. 0, 1, first qubit down, second qubit up. Qubit or spin is the same thing. 1, 0, first qubit up, second down. 1, 1, all the qubits are up, so are in the excited level. So this is a level, it's a basis of a 2 qubits, to describe the 2 qubits, the state of the 2 qubits. The density matrix is written like this. This is the density matrix that contains all the information about the state. I mean, literally all the physical information about the state, all the things that we can say as physicists. Yes?
One question might be a bit pedantic. You have two fermions. How do you distinguish between the fermions? How do you know which one is number 1 and which one is number 2?
No, it's a very good question, and it's because actually I think it's something that I maybe should clarify better in the paper as well. That is, I call them fermions in the sense that they satisfy the fermionic rules, in the sense that the operators before they were fermions, fermionic operators. But now I'm not saying that these things are indistinguishable particles. They are fermions, but let's say they are fermions. They are 2 different type of fermions. This is the point. It's like having 2 fermionic modes, if you want, and not that you have 1 fermion, that you have 2 fermions there. It's 2 different fermionic modes, but yes, it's a good point. So the density matrix is the object I use to describe the information I can talk about. And we write it like this. This 1, 1 means that in the element of the density matrix, in the ket, we have the state 1, 1, so double excitation. And this is the bra. After the comma, there is the bra. So, and this 1, 1. This is ket 1, 1, bra 1, 0. Okay. So these are the states there in the density matrix, in the ket and the bra of the density matrix. That is what we use to describe the system. Now I said that I need to write the Liouvillian superoperator as a bigger matrix acting on the density matrix. So you see the density matrix has 16 elements, 4 times 4. So what I do this thing, what is called the row order, something like that. So I write these 16 elements as a vector like this. This is from a 4 times 4 matrix to a 16-dimensional vector, like this, following this order. Okay. And now I'm ready to consider the Liouvillian superoperator here. The Liouvillian superoperator now is acting on this 16-dimensional vector. And, okay, recall the rule. The rule was that the number superoperator was counting the number of excitations in the ket minus the number of excitations in the bra. So I said here that in the density matrix, you read it as before the comma cat, after the comma bra. So now we can understand how to collect the elements of the density matrix according to the number superoperator. Because you see, in the red, it's the block associated to n equal to 0. And indeed, 1, 1 minus 1, 1, 0. 1, 0 minus 1, 0, 1 minus 1, 0, 0, and so on. Or the green block is n equal to 1. Indeed, you see 1, 1 minus 1, 0 equal 1, and so on. So you see that these elements now appear in the Liouvillian superoperator as a matrix as blocks, in the sense that where here it's white, you don't have nothing. So before it was a 16 times 16 matrix, the Liouvillian superoperator. Do you agree? Because the density matrix as a vector is 16, so the matrix that is acting on the vector that is 16 dimensional is 16 times 16. So now you can see that from a 16 times 16 matrix, because of this symmetry, I'm passing to a block here that is 6 times 6, these red elements of the density matrix. A block that is 4 times 4, that is the green. Another block that is 4 times 4, and is the conjugate of this block, so it's dependent on the other block, actually. I mean, in the sense that you can obtain it from the other block trivially. And then 2 single elements, 1 times 1 here. So the reduction of the complexity of the master equation is huge here, of course. And imagine that this can hold for not only for 2 qubits, but for instance, for n qubits in a common path, you have the same thing. So in the paper, there is actually a formula that is describing how the different blocks, the dimension of the different blocks, depending on the number of qubits and so on. But you see that when you have, I don't know, 20 qubits, the Liouvillian superoperator will be something that is totally impossible to write. Because it will be, okay, no, I'm not, well, something huge. But in this way, we can find some blocks which are treatable. And finally, I was mentioning before the steady state, the equilibrium state. We know that the equilibrium state of a system must be in this form, in which it has, like, let's say that I take this system, I make it evolve, and I get to the equilibrium at infinite time with my Liouvillian superoperator. So I know that the equilibrium state will only have the red elements here, in the sense that the equilibrium state cannot have, in the density matrix, elements which are not of the block n equal to 0. So the green one, the purple, the blue, the orange must disappear. Yes?
So only if you have one steady state, or is you
Exactly. If you have a unique steady state, it happens this. And now I explain you why. Because just to like, let's do a reductio ab absurdo, and suppose that you have a steady state that is unique, but has elements which are green. For instance, that you have the green and blue elements in the steady state. Well, then I can build a new state that is identical to the one before, so that has the same red part of the one before, but I set to 0 the green and the blue elements. I set them to 0. But since I'm removing coherences from a physical state, I'm still getting a physical state, because coherence, I mean, for the mathematical laws that tell me when this is a physical state, I'm still having a physical state. But then all the blocks are independent, so the Liouvillian superoperator applied on the steady state must give 0. So each block, the red block on the red elements must give 0. The green block on the green elements must give 0 on the steady state. But so the new state I've constructed by removing coherences must be 0 as well when the superoperator applies. So it means that it's a steady state as well. And so there is not a unique steady state anymore, because I have just built 2. So if there is a unique steady state, it must only have the red elements. And this is it is quite interesting also for fundamental reasons, in the sense that somebody you know that somehow you should get something that is the state of Gibbs, that would be the diagonal state for infinite number of particles, but here you are not getting it. So there is still a step that is missing here in the description of a
Besides of the steady states, I mean, is it works for any time evolution? Like, for example, for relaxation, is it I'm really confused because if you start with the one state and in time you end up with relaxation of zero state.
yeah.
But how does it describe the relaxation?
No, it's true. This is a would be a theorem about the possibility of existence. I'm not giving you the steady state in the sense that you're right. You start with the excited state, you said, and you go to the ground state. You were mentioning this relaxation.
Yeah, but L seems to be doesn't describe transition from the n equals 2 to the n equals 0.
Yeah, the existing elements 1, 1, 1, 1, and 0, 0, 0, 0 belong to the same block.
Yeah. Sorry. Okay. No, because I mean, this block is full. You know, this is the red block that is saying which elements are connected by the Liouvillian superoperator. So I'm saying, by putting the same color, I'm saying that this element is connected to this, and of course you do relaxation.
What is number? I think I'm confused what is number there.
Number?
1, 1, 1, and 0, 0, 0, 0 is same number. I mean, 1, 1.
No, yeah, because it's the superoperator. It's not, this is the point. It's not the operator. It's the superoperator. The superoperator is this. That is, you count the number of particles in the cat, and you remove the number of particles in the bra. So here is 1, 1 minus 1, 1. Number superoperator 0, right? No, I mean just believe to my rule. That is, you count the number of particles in the cat.
Plus 1 minus 1 minus 1.
Yeah, like if you have the excited state, so you are in the state, right? 1, 1. So the density matrix is written like this: 1, 1, 1, 1. My rule here is n applied to row S. You have to count and you say, here, how many excitations? You see, this is a superoperator, eh? It's not. It's different from the operator. They are also mathematically different. Okay, here it's very bad, but there is calligraphic and not calligraphic. You see the difference between this and this. This superoperator is you count the number of particles here, and you remove the number of particles here. So it's 1, 1 minus 1, 1 rho S, but this is 0. So this is 0. Do you agree? And if you take a new state that is ground state, well, it's the same thing. N calligraphic applied on the ground state is 0, 0 minus 0. Well, so they have the same eigenvalue. So they are connected in the master equation. But of course, as I said when I was mentioning the laser that is dissipating, and so you cannot do the experiments about reservoir computing and so on. That was the point. Here, the number operator is not conserved in the sense that, of course, if you apply the number operator, if you take the mean value of the number operator on rho S, here you get 1. There is 1. No, you get 2. Because there are 2 excitations. Right? In the up state, there are 2 excitations. But if you do it for the ground state, there is 0. So you see, there is an operator that has different value there, but the superoperator has the same value, and this is the point. The superoperator is literally in a higher dimension. Super because it's mathematically something that is acting on the operator. I mean, they are different objects. You don't believe in superoperators. You have never seen one in the I mean, you see, I mean, you can just forget about physics. You can think about it this like mathematics. It's a linear map defined like this, and has those rules. And I mean, it's defined like this with a commutator, and it's a linear map. And if you check, it has these rules, and it connects these parts of the density matrix. Well, in any case, same color means that they are connected. Different colors that they are not. So talking about relaxation, it means that, of course, the excited state is connected to the ground state. So, of course, you can relax to the ground state. But you're not touching these elements. So you're not creating coherences, if you want, apart from these two ones. You're not creating these coherences because of relaxation. This is the message of these colors. And so, well, okay, it's very late, and more or less this is it. Just some outlook. We want to use this symmetry to do something useful, indeed. So, for instance, to study phenomena of synchronization between the qubits I was showing at the very beginning in this setup of Aalto University, for instance, in which we want to understand, because, for instance, the synchronization, you can show that it's all contained in the block n equal to 1. So it's something different from the steady state. You see, you can use the symmetry to tell something physical that is not just mathematical. Then we would like, on the mathematical side, we would like to find a sort of generalization of a theorem for steady states which are not unical. So what happens when you have more than one steady state? Can you say something about the structure in the blocks here of this of all the family of steady states? Is something that is not clear. Then there is a possible extension to non-Markovian master equations in which you have to consider memory effects. So you have to understand that there is a backup between the effect of the environment and the evolution. And finally, we would like, okay, to employ the symmetry as it is as a way of reducing the complexity of the master equation of this differential equation. For instance, by implementing it in a suitable library like Qtip, that is a library of Python. And so, yeah, this is all. Thank you. Javi?
Yes, like I didn't understand if this symmetry is an induced or an artifact or your secular approximation.
Exactly. This is the point that tells you that in a certain way it's a mathematical artifact. Because it's true. I mean, it's something that is not physical anymore. I mean, because the fact that you choose to do a partial secular approximation induces you the symmetry. Otherwise, you will not have it. Because, well, you can see that when you write it down, you have terms which are mixing up this number superoperator, and you don't have a symmetry. And so this is the point. I mean, one question would be, can you recover a sort of physical sense at the higher level? So just let's suppose that you go to the sense, to the level of environment, system plus environment. Now, so you recover everything. You are not considering the open system, but the closed system of system plus environment. Can you find a symmetry there that is the equivalent of this symmetry? I don't think so, but maybe there are connections. But it's something that is not clear. Actually, this thing of symmetries in open systems is not something well studied. I mean, the theorem I mentioned before, it was of 2014. So there are a lot of things that are still there to study.
I was going to ask, like, how fundamental was this approximation? Like,
I mean, it's...
The approximation is valid in some regime,
yeah.
so it's physical in that sense.
Yeah.
You say, okay, I do it in this way, and then I have this beautiful superoperator symmetry. No, you have a regime in which you will have to be unavoidably in
and in this regime, where were your assumptions? No?
Exactly, exactly. When I discuss the model and I say the light coming out of a flying disk is to say that is a regime in which you can do the partial circular.
Situation in which you cannot apply.
You cannot apply, but still the point of Javi.
So you can neglect these terms of the data, and then in that regime, so you need to search for other superoperators.
But still, you may also choose not to do the circular approximation, and of course, you are not doing something wrong. I mean, you are not doing an approximation, it's fine.
It's fine, but you cannot apply these.
But you don't have a symmetry. So the symmetry is, in that sense, mathematical for me.
In the real density method, there is up to the an error that you can
In a
control.
sense, it's just
Yes,
you are,
yes,
you are
yes.
just dummy and you are not seeing it. But if you calculate the object, all these pieces that are beyond the symmetry will be small. Because
Yes,
only-
yes, of course, yes.
Not only
Mm.
mathematical.
No. Yeah, yeah. I mean, no, it's true, but I say it's not so clear for me. No, of course, it's totally true what you say, but it's not so clear whether there is a fundamental physical reason behind or not. If there is a higher symmetry or not, let's say.
Yes.
I don't know. I don't know. Yeah. Okay.
Okay, ciao.
I don't know. How to stop? Eh?
Devo andare a Palma.
Ah, ok.
Quindi se due commenti te li faccio dopo.
Sì.
Perché devo scendere per andare in banca.
Va bene. Come si ferma qua la roba?
Creo que habla con los informáticos por lo menos.
I just go to talk with informatics to stop the recording.